And so today I'll be giving a mini talk on essentially orchestrating modern implants with LLVM. I come from the Orchestrating Research Development team alongside my colleague Steven Salinas. So to get into it, so why should you care essentially about orchestrating modern implants with LLVM? My primary motivations, and then an introduction to LLVM, essentially what is LLVM itself, how LLVM itself is architected, and then some examples of existing case studies, and then examples I want to implement, particularly for my own uses and for why Orchestrating is particularly focusing on this as a research area. And then a minor demo of essentially one of the passes I ended up implementing thus far as part of our internal compiler toolchain. So why should you care? End of the day, trying to essentially deal with one of the biggest problems with that customers are primarily dealing with one of the complaints we get with typically centered around static and behavioral detections, like for example YARA signatures, or an endpoint detection software catches the way we particularly may perform an action like loading an object file, loading a DLL, etc. This allows the framework allows me to do this, and then essentially a lot of the tradecraft implementations out there, such as like stack spoofing, sleep masking, etc., they're particularly designed for one particular file format, such as beacon object files, DLL formats, or they may be constricted particularly to shellcodes and don't work too well when you try to implement them inside a DLL or portable executable. And then essentially there are so many disjointed implementations out there that I have observed in particular where a lot of them tax back into this fact that they're all disjointed. There's like, they only work from some particular file formats. I want to develop something to where I implement one pass for all of our tradecraft implementations. I enable it, I can just embed it inside of there, and then it's available to no matter whether you want to operate with DLLs, running inline Ps in memory, DLLs, shellcode, etc. And then, get on to the next thing. So, my motivations. A lot of the existing research don't really go beyond obfuscation. Let's think, the particular reason why is a lot of them were particularly focused on essentially breaking, hindering reverse engineering efforts, like for example the obfuscator LLVM implementations that jump-started all the efforts over the years that was originally done by the current Snapchat development team. Their method was they wanted to essentially protect a particular API component within their within the Android app that they and in their case they have to end up going with the LLVM approach. Additionally, majority of the implementations are not exactly designed with a flat executable, with the idea of a flat executable or a position embedded code, as is known as. In reality, a lot of them are designed, for example, I would say obfuscator and LLVM in particular, will rely on having a readable, writable section of memory that you can overwrite, so it can write to, for example, for global encryption, for string encryption. I want to be able to have it to where I can have it for any file format, with the only assumption that it works with readable and executable code. So that means it's a little more flexible. You can embed inside of a .text section, and it just works with shellcodes, with PEs, doesn't matter. And then essentially having our own LLVM tooling is inherently a huge benefit for us because it actually enables us to perform some capabilities that otherwise would have been inherently impossible. Let's take, for example, sleep mask implementations. You can, for example, break, let's take for example, page fluctuation using LLVM by instrumenting it to execute certain functions. It would have been harder. I could have done it manually, but it would have been considerable pain otherwise when I could just tell it to say inject in the function entry and exit to perform the behavior and then do it all, and then it just works. So it's less effort for us as well to develop capabilities quicker for the users. So, to get into it, so the LLVM low-level virtual machine framework, or LLVM, was essentially a modern compiler framework developed by Chris Ladner as part of his master's thesis at the University of Illinois. His idea was he wanted a compiler framework that could essentially you don't have to develop your front-end language, your front-end parser that would translate to the LLVM or intermediary, so that you could then all the optimizations, translation to machine code, etc., is done with a common backend, so that instead of having 50 implementations out there, here's one. You do the easy part of implementing Elixir, you can move on to that part. So then, Clay, when he first implemented it, it was just an LLVM IR intermediary. When he was eventually hired by Apple, he developed the Clang as well as the Swift language, which then which allowed him to translate essentially the Swift language and C language and C++ language into this LLVM IR intermediary. It is actually often used by modern languages like Rust, Swift, Zig, etc. And it's considerably easier for them, like I've said, to implement a front end, Elixir, and then have a common backend that everybody is maintaining, developing, etc., performing common optimizations, etc. So, and my own colleague actually previously, he went as far as writing his own toy language to develop beacon object files as well. So again, the architecture is separated into essentially three components. The front end, the middle, intermediary, back end that essentially performs optimizations like optimization small, optimization fast on the LLVM or intermediary. These are typically what are known as module and function passes. They're designed on the LLVM or intermediary. The backend translates essentially into a target-specific. Once that optimization pipeline has occurred, it then translates it into target-specific machine, architecture-specific machine code, such as x86 assembly, AR64, etc. This is actually where you can implement your own machine function passes, where you can do, for example, implementing opaque predicates. You can implement a like jump code insertion pass there, like injecting NOPs. It doesn't matter. It's pretty flexible in that respect. So, get into it. So here's an example of generating IR from C using Clang. Yeah, let's go. Appreciate it. Let's go here. So we have let me see. So yeah, at the moment I have a mini project here that allows me to translate a full project into a complete LLVM or bitcode using whole program bitcode techniques that was documented, I think, in LLVM 19. So to get into it, 1 second. So to get into it, essentially, so we have this project here. It just prints. We have this project here. It essentially prints a message box, compile me, etc. Nothing too special. I have CMake here that essentially allows me to automate the whole build pipeline. Builds a whole program bitcode. If we then print the bitcode, message box, hello. We have here's the intermediary IR that I can then perform optimization, obfuscation, etc. with. So, switching back to the demo slides. So, to get back into it, one of the things I wanted to study was how can I want to look at existing implementations and think of how the ways I can improve it significantly on top of the other things I mentioned before. So right now, a lot of the major implementations are implemented as like obfuscation frameworks. Think, for example, Obfuscator LLVM. Those are like one of the most infamous ones in existence. Hikari, which is essentially another implementation iteration of Obfuscator LLVM. Polaris, Pluto. There is, for example, XVMP, which a gentleman had discovered a way, or came up with a creative way of essentially implementing a virtual machine translation language, specifically using LLVM, and then he would mutate add sub instructions, as well as I think a couple of arithmetic instructions, and virtualize the instructions, and then place them back, insert them back into the binary, and then as well as Goron, which is essentially just another Obfuscator LLVM implementation. There have been some other research recently with, for example, people building their own virtual machines. One of the most infamous examples was the one conducted by Secret Club. This was known as Risky VM. They essentially figured out they can simplify the development of virtual machines by essentially developing write their code, standard Windows code in x86 Windows code, develop a whole program bitcode like I had shown there, and then they could translate the x86 bitcode to something that would work with RISC-V specifically, and then extract the raw object link using GNU-LD, and then extract the raw RISC-V opcodes and then interpret that. There's another gentleman as well who did another implementation shortly thereafter called PSX Execute, who goes by the name of Eversince. It was a MIPS 32-bit implementation. It's pretty cool. It's one of another thing you could do with it, but get into it. It's one of the things I want to implement. So, in particular, on top of some of those things that we're exploring as part of the tradecraft options to give to customers, is I would essentially make developing position independent code a lot simpler. I'm somebody who has always developed kernel shell codes like double pulsar, etc., and I'm obsessed with it. The problem is it's a considerable pain to develop. It's not exactly user-friendly to do. You have to manually resolve functions, you have to sit there and have specific macros for strings, you have to have a get instruction pointer stub. It's not exactly user-friendly. It works well enough, but it's not exactly the best implementation. I essentially have so far got to the point to where I can translate into standard C code that I write as a normal portable executable into a position-dependent code object, including converting x86 absolute addressing into relative addressing without any specific macros or anything else, and getting rid of the get IP stub, which is actually originally a static inline stub that was in my templates that people can use to say, okay, fingerprint, this is possibly a position-dependent shellcode that should not be here. And then one of the other things we're exploring is, for example, mutation and polymorphic engine on the target level, so that signatures essentially become a non-existent issue to us. Like I mentioned before, using a module function pass and inserting like junk code, opaque predicates, something to also hinder, as well as we are developing more capabilities, as well as hinder the efforts of defenders as well as other competitors from being able to easily decompile and reverse engineer our capabilities so that we can, last a little bit longer than that. Other things I want to eventually get into, but we'll unfortunately get into that now. So let's get to the next part. So I'll show you an example of a string into integer constant mutation that I performed using particularly with a standard shellcode. So, thanks, buddy. So the next part, okay, so we switch back to our secondary demo. We have, so here's a standard shellcode template, one of the ones I ended up writing years ago. It prints, essentially does kernel 32, load library, user 32, you see all those fancy strings. So if we then run through and compile it, clean first, build it, run with no pass encryption, so we can compare the differences. See build shellcode. So if we see here, there's a very obvious string, load library, great, because that's one of the things I could say, okay, here, this payload is in kernel 32, etc. It's way too obvious. Now let's for example, we have a pass that runs in, encrypts those strings, and then we'll try to mutate any constant integers that I'm using. For example, the hashing algorithm, like I commonly use DJB2. Let's deal with the 5131 magic hash used for essentially for DJB2 specifically. So clean first. Compare that, runs the string encryption on it, and then if we print shellcode.bin. In this case, this pass will, in this current case, this pass then will take to locate any strings within the binary, encrypt them, move them to a stack copy, so it built it on the stack on demand rather than storing in the section that it has to pull from, and then it will essentially then replace all references within the current executable with this with the new encrypted copy. So it removes those strings, deals with that problem. So that's just a simple example. So, yeah. What am I doing? No, I think it's yeah. Okay, on to the next slide. So, it's a little bit of a rushed one, but is there any comments, questions, and concerns? That's essentially, my name is Austin Hudson. This is Orchestrating Modern Implants with LLVM.